So, welcome to all and good afternoon. Today we will start with another session which will be related to the M-derived band pass filter and M-derived band stop filter. So, let me remind you that in the last class we were talking about the M-derived filters, and we have so far covered the low pass filter and the high pass filter. Now, I just want to share one slide. In the last class, there was some problem in the slide. So I like to share that slide with you. Okay, that was the slide that we were discussing about the M-derived high-pass filter, and I have given a wrong diagram. I have corrected it. Okay, so just inverse type of phenomena is there in the high-pass filter, as you know. In the same is the case in the constant K filter. So here it will be not L by M. It is twice C by M, and here it is also twice C by M. And here the shunt arm will consist of L by M and 4M 1 minus M square C. This is the T section and the pi section. Okay, so I will be sending you this PPT to your Google Classroom. So I just want to correct it, that how it will look like. Okay, now today we will start with the M derived band pass filter. Okay, now we all know about the prototype constant K M derived band pass filter. So let me revise that also. You all know that this was the situation. So just quickly I run this PPT. Okay, what you have learned in the prototype band pass filter. Okay, you see that this was the case. Okay, sorry 1 minute. So you can see. So that's how the low pass filter and high pass filter will combine together to form a band pass filter. And this was the diagrammatic representation or the network of the T and pi section of a T and pi section of band pass filter. Okay. So you can see that in the T section, let us concentrate on the T section. There was L1 by 2 twice C1 and twice C1 and L1 by 2 on the two half section. And there was the L2 and C2 components were there in the shunt arm, which are connected in parallel. Okay. So with this background, okay, let us come to the and we have considered that the resonance phenomena will be there. Okay. Like this, we have found out everything. So this is just for your sake. I have run this slide. Now let us come to the M derived band pass filter. How it will look like. Again, this is being formed by combining the M derived low pass and the M derived high pass filter. Okay. So in the series arm, what we will get? We will get M manual by 2 because of the low pass filter, and also twice C1 by M because of the high pass filter. So there will be two sections, two half sections on the series arm. So the same is being repeated on the right hand side and on the left hand side. Okay, so ML1 by 2 twice C1M and twice C1M ML by 1 2 two half sections are there in the series arm. Now, as far as the shunt arm is concerned, we know that the shunt arm in a case of the M-derived filters. If you remember the fundamentals of the M-derived filter, then you find that the T section will consisting of Z2 by M plus 1 minus M square upon 4M into Z1. Okay. So we will just substitute the value. Okay. And we will get this arm. This is the shunt arm. Okay. So what we will get? We will get L1 component also, a C1 component also, and the L2 by M and MC2 are in parallel, while the L1 with 1 minus M square upon 4M and C1 with the value 4M upon 1 minus M square, okay, will be in series with each other, while MC2, L2 by M are in parallel with each other. Okay. So again, we will now in case of the so-called the M-derived filters, we also find out a frequency of infinite attenuation. Now this frequency of infinite attenuation, then later on in the fundamentals we have told that the this frequency of infinite attenuation will provide the sharp attenuation not near, not exactly at that cutoff frequency, but near the cutoff frequency. Okay, so here you will suppose, because it is a band pass filter. So if you remember the diagram, I'm just drawing the diagram. Is my voice is okay now? Is my voice is okay now?
Yes, sir.
Okay. I think so. Now it should be okay, huh? Okay. So, uh, as I've already told you that while going through the fundamentals of the M-derived filters, we have to consider an F attenuated frequency. But in band pass filter, you will find that there will be, this is a band pass. So there will be two cutoff frequency, no doubt, FC1 and FC2. Okay. So definitely we required one attenuation frequency. So there will be two, first of all, there will be two stop band. One is this and another is this. Okay. What we want in the stop band, the attenuation should be infinite. The attenuation should be infinite. So the attenuation here also should be infinite. Attenuation here also it should be infinite. Okay, so we require two cutoff frequency, and we'll found that there will be two uh, frequency of attenuation. One is f1 infinity and one will be f2 infinity. The f1 infinity will be near the cutoff frequency f1, or you can say as a fc1, and there will be two the second frequency of attenuation will be near to the f2. Okay, and we will not go into the detailed mathematics juggleries. Okay, it is same as we have derived for the other things. So directly we will get the result that the resonance frequency, now definitely resonance will occur, then we will assume that our resonance will occur uh, will be same. Resonance frequency will be same for all type of resonance, whether it is series resonance or the shunt resonance. Okay, and it will come out to be the geometric mean of the frequency of infinite attenuation. Also, it is a geometric mean of the two cutoff frequency. So f0 is equal to under root f1 infinity into f2 infinity is also equal to under root f1 into f2. So this is equation, you have to remember it. Okay, then the another equation on the fundamental basis of the M derived filters, which you have gone in the very first slides of the M derived filters, we can also write down that the f2 infinity minus f1 infinity is equal to nothing but f2 minus f1 upon under root 1 minus s square. So this formula, this is very easy formula, is in fact it is true for all types of filters, all type of M derived filters. Okay, and but you will find that in band pass filter, the another relationship between the cutoff frequency and the resonant cutoff frequency and frequency of infinite attenuation is f2 infinity minus f1 infinity is equal to the difference of the two cutoff frequency divided by under root 1 minus m square. Okay. So with this, we can find out the value of m, and the m comes out to be like this. Just mathematical rearrangement is there, and m comes out to be under root 1 minus f2 minus f1 upon f2 infinity minus f1 infinity. Okay. So this is the formula which you have to remember. If you can't remember this big one, then it is better to remember this formula. Okay. Regarding the band reject filter and band pass filter, there is a slight modification in this formula. Equation number 3 formula, there is slight change is there. So you have to take into consideration that slight change, otherwise the things remain same. Okay, so you can now just manipulate it, and once you are giving the value of f2, f1 and the two infinite attenuation frequency and two cutoff frequency, you can easily find out the m. Okay, so this is a variation of the character impedance, the variation of the attenuation, the variation of the phase shift with respect to the frequency. So now you can see that this is the resonance frequency, this is the f1 is the cutoff frequency, this f2 is the cutoff frequency. So we are getting an approximately an infinite attenuation in the stop band. Here also, though there is a gap is there, Okay, but somehow we are getting after a cutoff frequency, we are getting a very high infinite attenuation, which is desirable. Now, it depends upon the design engineer how he sets these two frequency. It should be placed very near to the two cutoff frequency. Similarly, phase shift is clear that you can see the variation of the phase shift. It is plus pi beyond the cutoff frequency. Now, next, I directly switch over to the M derived band stop filter. Okay, because the you should not confuse with the formula. Okay, and also to the diagram. Diagram is also very clear. Here also, whatever is series will become shunt, and whatever is shunt is will become series. The same thing as we have derived in the band reject filter. Okay, so here the two section ML1 by 2 and twice C1 by M. Okay, now you can see compare. In case of, because generally such type of confusion arises during the examination. Okay, what should be there? So once the concept is clear, now here both are connected in series. Here both are connected in the series arm in parallel. You can see ML1 by 2 and twice C1 by M. They are connected in parallel. Similarly, for the other half section, ML1 by 2 and twice C1 by M are connected in parallel, though they are present in the series arm. Now, as far as the shunt arm is concerned, now see, compare with this. Here L1, here L2 by M and MC2 are connected in parallel. But now see what is there in this. Okay, L2 by M and MC2 are in series, while they were in that case they were in parallel. You can L2 by M and MC2. So L2 by M, MC2, they are in now in series. Okay. So whatever is what there was in parallel became series, and whatever in series they became parallel. So in that case, 4m upon 1 minus m square C1 and 1 minus m square upon 4m L1 were in series. But now they both will be connected in parallel, and in this way the shunt armies get completed. Again, it will have two cutoff frequency. Okay, because it is also band reject filter. So if I will draw the diagram of the band reject filter, if you remember, band rejector means it reject a particular band of frequency. So below FC1 it passes all the frequency, and above FC2 it passes all the frequency. Okay, now here again we want and cutoff two frequency of infinite attenuation. Okay, because attenuation is required here. Okay, so again there will be two infinite attenuation. One will be near to FC1 and another will be near to FC2. Okay, now here I have not written FC1, simply F1 and F2. So don't get confused with my words and whatever written is there. F1 is same as that FC1, what I am telling as FC1, and F2 is same as what I am telling as FC2. So now these are the two infinite attenuation frequency. Now here you will find a slight difference. Okay, the formula that is of the geometric mean is same, but the formula which is establishing relationship between finite attenuation and the cutoff frequency with M is different. You can see, check. Here it was F2 infinity minus F1 infinity, F2 minus F1 upon under root 1 minus m square. Here there is slight difference is there. It is f2 infinity minus f1 infinity is equal to f2 minus f1 into under root 1 minus m square. Previously in band pass filter it was in denominator, but in the band reject filter it is in the numerator. Okay, and accordingly if the four frequencies are given to you, you can easily calculate the value of m. Okay, so like this manipulation has been made. Okay, and you can see this manipulations. Okay, then you can calculate the value of m. So I just don't remember the manipulation formula. Okay, just remember this formula. Okay, so with the help of this formula you can easily calculate the value of m, and accordingly you can design the parameters. So this is again a graph which is representing the variation of the characteristic impedance, attenuation constant and phase constant with the frequency. Again, you can see these are the two cutoff frequencies, F1 and F2. There lies the band stop filter, and there you are obtaining the infinite attenuation at the frequency of infinite attenuation. Okay, so just the graphs are depicting that yes, whatever for whatever purpose we are designing the system, we are getting that desired output. Okay, so today I will upload these things to your Google Classroom. Okay, tomorrow what we will do, that we will tomorrow completely devote our whole session to the numericals, starting from m derived high pass, m derived low pass, m derived band pass, and band reject filters. So what is today's your assignment is that today you go through this all these things, just have a revision. Okay, just put all this formula in one paper. What is formula for the band for prototype, and how it get changes when it became a m derived filters. Only you have to remember the value of m. Okay, m for a low pass filter, m for high pass filter, m for band stop filter, and m for m pass filter, band pass filter. Okay, so once you calculate the m, okay, you can easily find out, if you know the, you can easily find out the parameter value l and c, because you know the values of the l and c through the prototype constant filter. Okay, so that's all for today. I'm not taking too much time. Okay, just I will upload this on the Google Classroom, and your work is to just go through it and just get ready with the formulas, because tomorrow we will get we will do the numericals, so many numericals. Okay, so that immediately when I put a numeric formula, you should remember, oh, this is the formula is there. Okay, otherwise what happens, I keep on solving the numericals or giving you the numerical on the slide, but you don't know about the formula. So what you do, that today from all my slides you just prepare a table, and through that table just write down all the formulas related to high pass, low pass, band pass, and band stop filter, and then immediately you will come to know that what the things are there. Okay, so today the session is short. I'm leaving here. Okay, if you have any doubt, then you can write down the chat box. Okay, so your today assignment is that get ready with all the formulas which I have given it. I will upload the PPT today. Okay, and tomorrow you should be ready with the formulas. Okay, with the numericals. Okay, that I will immediately give you numerical and solve it through on my slide, and you should get ready with the formula so that there is no confusion is there. Thank you very much.